Yeah, good afternoon, everyone. It's my pleasure to present my work here. So I'll be taking you all the way to the large-scale structures now from the solar work that Piali presented. So this is my group at NCRA currently. So we have one postdoc, Samir Salunke, and two PhD candidates, Ramananda and Arpan. And I'm also co-supervising two PhD students one at Christ University and another at Kashmir University. So to introduce the large scales that I'll be talking about, so I'll be talking about galaxy clusters. So as we understand in the, what we understand about the structure formation in the universe, smaller structures form first and they merge to form larger structures. So galaxy clusters are among the youngest of these structures. They have evolved to become very massive. So they are the largest gravitationally bound structures in the universe. They span of the order of a megaparsec cube in their volume. They have masses of the order of 10 raised to 14 to 10 raised to 15 solar masses and contain hundreds of thousands of galaxies. And if you look at the mass distribution in a typical galaxy cluster, you'd realize that most of the mass is actually dark matter. And the small percentage which consists of baryons, sorry, excuse me, when the galaxies form actually a very tiny percentage of the order of few percent. And most of the baryonic mass is actually in the diffuse medium called the intracluster medium. The intracluster medium is mainly thermal plasma, and you have electron densities of the order of 10 raised to minus 2 to 10 raised to minus 4 centimeter cube. So if we look at galaxy clusters across wavelengths, because our goal is to understand the physics mainly in the intercluster medium. And of course, we are not limited to any particular wave band. We want to address the physics, and we would want to observe in any band that will help us understand this physics. So if you look at galaxy clusters across the electromagnetic spectrum, in optical, you see the stellar light from the stars in the galaxies in a galaxy cluster. And if you look at the same cluster in X-rays, you'll find that this intracluster medium, this hot thermal plasma, is emitting thermal bremsstrahlung, and it is an extended source in X-ray emission. Now the question is, what happens in radio bands? So there are elusive components of the ICM which were not basically did not show up when you looked at the cluster in optical or X-rays. So that is what we see in radio bands. So magnetic fields and relativistic electrons in the intracluster medium lead to sources of synchrotron origin, and they manifest as extended diffuse radio sources which are not associated with individual galaxies but with the intracluster medium itself. These are termed as radio halos when they are centrally located in a cluster and have more or less the morphology of the extended X-ray emission. And there are other kind of diffuse radio sources which are extended and elongated and located mainly at the peripheries of galaxy clusters called the radio relics. Basically, these different sources are representing different phenomena in the intracluster medium, and we can basically probe the physics of these phenomena using these radio sources as tracers. So here, when I pointed out the radio halos, halo and the peripheral relics, this is a famous cluster which has diffuse radio emission of both the kinds in the same cluster, but that is not always true. You have clusters which have only radio halos, which have, for example, only radio relics, or a combination, or even a more complicated system where you cannot classify the emission into these particular categories. The intercluster medium physics that we are trying to probe is quite complicated. So you have this intercluster medium, which is a high beta plasma. So beta is this ratio here, the ratio of pressures. And as compared to the solar plasma, for example, in the corona. This is a high beta plasma. So you have processes like AGN and galaxy feedback. So the galaxies in the galaxy cluster are also playing a role in driving the physics in the surrounding medium, which is the intercluster medium. So AGN and galaxy feedback is also important. You have other processes which are affected by the presence of magnetic field. So overall in a plasma, because of the magnetic fields and the coupling of the particles and the magnetic field, the transport processes are affected. So we use radio halos and relics as observables to probe these phenomena. So some of the questions that we try to address are basically how do we accelerate electrons in the intercluster medium to become relativistic. So we know that there is copious amount of X-rays emitted by the thermal electrons. But where do we get these relativistic electrons which are present all over the cluster? What we know is that a source like a radio galaxy, which is a single source of, let's say there are jets and you have relativistic a plasma coming out, these electrons will lose energy very fast because of the losses, because of synchrotron emission, because of inverse Compton and so on, and it won't last. So you won't have the time to distribute these relativistic electrons from a single radio galaxy all over the cluster. So you will need to find some process which is in situ accelerating the particles all over the galaxy cluster. So one of the things that has emerged from observations is that the presence of radio halos and relics is preferentially in clusters where there is a recent merger. So as we know, structures grow by mergers. So galaxy clusters are not sort of settled structures. They're evolving by the mergers of groups and other subclusters and so on. So this process of merger leads to injected turbulence in the intercluster medium and also drives shocks. And these are the phenomena behind the origin of radio halos and relics. And then the question is, do we understand the presence of this relativistic plasma and magnetic fields in the clusters as a function of redshift? Do we know how that evolves? So towards that, today I'll be presenting a couple of recent results from our group. So first is a study of a very high redshift. A high redshift in galaxy clusters context is of the order of 1. So this 0.87 is quite a high redshift galaxy cluster. It's called El Gordo. And the interesting thing was, if you look at the cluster in X-rays, shown in color over here, the cluster has a bright core, and the emission sort of extends into two tail-like structures on one side. So this is a signature of a disturbance from a relaxed system. It's clearly a merging cluster. And when you look at it in radio, the contours represent the radio emission over here. You see presence of central radio halo emission as well as presence of elongated structures at the peripheries, which are relics. So these were discovered back in 2014 using radio observations. What we did was a much deeper study with the upgraded GMRT at 400 and 650 megahertz and also much deeper Chandra X-ray bands. So one of the interesting thing about high redshift clusters is that the inverse Compton losses, because of the higher density of the CMB photons at that redshift, you actually would require the acceleration efficiency or the any mechanism which is actually producing the relativistic electrons to be operating at much higher efficiency, because the energy loss rate is much higher. And the inverse Compton losses really, they scale as 1 plus e to the power 4. So as you go to higher redshift, you are going to face much higher losses. So it was when it was discovered, it was a surprise radio halo. Nobody would have expected that there would be a radio halo of similar brightness and power as compared to the nearby radio halos. So we did a deep study of this recently. We produced spectral index maps. So you do a resolved spectral index across the source in order to look at the age of the electrons across the source and infer about what is the driving mechanism. So we could quantify this is a spectral index map that we produced. We also could do a little more with the Chandra X-ray data that we had. The X-ray surface brightness, basically from that, if you have deep enough observations, you can translate it to a density fluctuation power spectrum. And the peak of that power spectrum can be used to relate it to turbulence, the turbulent Mach number, and so on. Of course, there are a number of uncertainties in the process because to translate the observational numbers into, into a 3D, representation makes a lot of assumptions. But this was an interesting avenue we explored, and we could come up with understanding of what the turbulent energy is involved in the reacceleration of electrons. So we came up and outlined what are the challenges in understanding the acceleration efficiency in this turbulent reacceleration. Just to compare with the statistics of the known high redshift clusters, this is a plot of radio power versus mass of the cluster for a sample of of clusters with known radio halos. And you can see the sample has evolved quite a bit. There are a number of clusters, and Elgato sits over here. It's the brightest among the brightest radio halos. And it is also a southern cluster and falls very conveniently for the square kilometer array observatory, which I'll talk about in a bit. We are looking at this object as a test case for the SKA as well. Moving on to other results, I'll briefly mention a couple of other results. So radio halos are described as centrally located sources. They trace, they have a morphology similar to the thermal medium. So we try to look at the correlation between the thermal and non-thermal electron density distribution and so on. But as the sensitivity of the telescopes is going up, for example, with the LOFAR in recent years, when one looked at these some clusters with LOFAR, it was found that there was much more emission beyond the known radio halos, which basically is something that envelops the radio halo. And if you look at the profile of the radio emission in the cluster and plot it, basically, there is a basically this function which describes the profile of a classical radio halo. And there is this extended envelope which is shown by this flattening profile. These are termed as mega halos. There were 4 which were presented. Sorry, this is 2022. And then, so this was the power of going to much lower frequencies and having the advantage of very short baselines which are capable of imaging this very extended faint emission. So the curiosity is what are the kind of spectral indices of these sources and so on. So you also, you can't do with just one frequency measurement. You need measurements at other frequencies and matching the kind of sensitivities you have for extended sources at lower frequencies. Similarly, at higher frequencies, it gets more difficult. But we attempted this experiment with the GMRT to see if we could actually find emission beyond radio halos in a cluster. And that is what we did in this particular cluster. So these deep UGMRT observations led us to find this extended envelope of radio emission surrounding the radio halo in this particular Planck cluster. The size of this emission is about 3.2 megaparsec. And this is the first mega halo to be discovered at any higher frequency than LOFAR. So we also explored the profile and so on. And we found that, so we proposed this as a candidate mega halo. And we could also constrain the spectral index and so on. Moving on to another highlight from our recent work. Relics, as I mentioned, these are peripheral elongated arc-like sources. So they are basically tracing the shocks that form when clusters merge. So these outgoing shocks So basically, when two subclusters merge, the intracluster medium in these two subclusters is weakly collisional. So the intracluster medium experiences all these physical phenomena. And the discontinuities basically develop into shocks at the peripheries where the electron density is much lower and your sound speed is basically lower. So you have the chance of making shocks at the peripheries. So in this particular, so the polarization of relics is also important because it traces how the shock, basically because of the shock, there is an alignment of the magnetic field along the relic. And this allows you to also constrain other things in the underlying shock in the relics, because at these peripheral locations, X-ray observations are not very effective because the electron densities are so low, it is very difficult to detect shocks in the cluster outskirt in X-rays. One thing to understand about this is that we know that relics are polarized at mostly 1400 megahertz because that is where most of the measurements have been done so far. At lower frequencies, we know that it will be difficult to detect polarization from relics because there will be depolarization because of various effects that come into picture as you go to lower and lower frequencies. But it is not clear whether we understand all those processes. So going by what we understand as the process of depolarization, we would be expecting a certain level of lower polarization at sub-gigahertz frequencies. But until we measure it, we will not be sure whether what we understand about the depolarization is true. So we set out to measure this polarization. So this is the first measurement towards any relic at a sub-gigahertz frequency that we managed with the upgraded GMRT. So this was the northwestern relic in this cluster, Abel 746. And we measured the polarization, and by combining it with the WSRT data at 1400 megahertz, we could make some models for what we understand about the depolarization. So if you look at the linear polarization fraction as a function of wavelength, the blue points here show the linear polarized fraction. And these curves basically try to fit a model over there. So if you see these red points, they're at the higher frequencies, the ones which came from the WSRT. This is from the GMRT. And what you can find is that it is not a smooth depolarization curve, but there are these features which we do not understand fully. So there's much more to understanding the depolarization than what we know. So I would like to quickly now mention these measurements which I have presented about extended sources or making polarization measurements at very low sub-gigahertz frequencies. All this comes with a lot of technical expertise behind the data analysis. And in the current times where our telescopes have increased their sensitivities by going to much wider band coverage or instantaneous bandwidth, we need automation in our data analysis as well. So in that pursuit, I have put up a pipeline called Capture, which came out back in 2021. And we are going forward in the development of this pipeline. And the new version is expected to come maybe later this year or early next year. So in this pursuit, that's another aspect of research that I would like to present that I have gotten into in the past few years. So square kilometer array observatory is basically basically we would like to build the largest radio telescope ever built. It's a consortium of 13 countries, and India is a full member. This will be basically, this will have two components, SKA mid and SKA low. Mid based in South Africa and low based in Australia. So it is going to be a very sensitive radio telescope when it completes. And the timeline roughly is at this point over here, where the SANS verification will start in the towards the later half of the next year. This was an image released from the SKA observatory this year, early this year, where they have put up the image made from 4 stations which have started operations. in Australia. India is part of the SK, and we are making contributions to the science data processing pipeline. This effort is basically a collaboration between academics, about radio astronomers, and the industry. There are about 8 to 9 teams under the SK science data processing spread across the member countries. I'm leading the team from India called Team Dhruva, and we have industry partners, ThoughtWorks and Persistent Systems Limited. This is our recent picture from the SK headquarters. So what we're doing is we are building components of the pipeline which will eventually be used to analyze the SK data. So the challenges there are basically in scaling. So let's say we know the methods that we need to analyze these data. However, to make those methods work at the kind of sizes of the data that will come from SK is a big challenge. And that is where the collaboration with industry is playing a role, because they bring in this expertise in distributed computing, which we use to make our pipelines optimized in that way. So under Team Dhruva, we have responsibilities of building the instrumental calibration pipeline, the spectral line imaging pipeline, and we also have the overall responsibility of stringing together all the component pipelines into single end-to-end flow. So to give you a very quick update, we've been continuing our work on these pipelines over the past 1.5 years. And the latest news is that we've successfully run the instrumental calibration on the commissioning data. And that is as, as latest it can get. Just the last week, we finally succeeded in, checking all the boxes that we are doing in the right things. So the times are getting very exciting. We are working closely with the commissioning team of the SK Low, and we hope to validate these pipelines with more data as new stations will be built and added to the existing array. So I'll just quickly summarize in a moment. So in galaxy cluster science, radio bands are helping to understand the acceleration mechanisms. We want to look at high redshift and understand the evolution from then on to now, and the presence of a new kind of faint radio sources to understand the acceleration mechanisms. We have measured the polarization at sub-gigahertz frequencies, and it has opened new possibilities, and we will be doing it for more number of radio relics now. We have the data analysis pipelines for the GMRT, which we are also updating soon. And our work on the SK observatory is ongoing. Team Dhruva from India is leading the spectral line instrumental calibration and end-to-end pipelines. And we hope to see more results coming over the next few months. And I'll stop there. Thank you.
Thank you, Ruta. Very exciting work from UGMRT and also exciting news from SKA. Any questions for Ruta? Yeah.
Hi, Ruta. Thank you for the nice talk. Could you please make some comments on the nature of plasma and magnetic fields in these mega halos as compared to the ordinary halos? Because the radio intensity that you showed seemed to be very different for both of them.
You mean the profile? Yeah. So one thing that is So what we try to look at is the correlation between the distribution of the thermal plasma and the non-thermal plasma. So you look at the density profile of the thermal gas, and then you compare it with what you expect, what is seen in the non-thermal. So we do you can do point-to-point correlation between the surface brightness of thermal and non-thermal, and that can actually constrain the theoretical models. So this envelope is, the origin of these radio halos is, like I said, is related to mergers and the turbulence that is injected during a merger. But it is unclear because there are examples of radio halos present in clusters which do not show any obvious sign of mergers. So there is a competing model, or I would say another contributing factor which could be working alongside the turbulent reacceleration, which has an origin in the hadronic collisions or the proton-proton collisions in the intracluster medium. And that is expected to be present in all the clusters because you would have relativistic protons clusters present throughout the evolution of the cluster as it evolves, and the protons will not lose energy very fast like electrons, and they'll survive in the medium. And these processes can again lead to a secondary electron population, which can give rise to radio emission. So one of the quest is also to look at these off-state clusters where the contribution may be mainly coming from these hadronic processes rather than augmented by these merging systems. But in this case, where there is a profile change, one of the ideas is that whether this contribution is coming from any of these other processes which may be present all over the cluster, because this is very faint as compared to the classical radio halo. The other things people are also exploring are the self-interacting dark matter. So this can also lead to a population of relativistic electrons, which in presence of magnetic fields can emit synchrotron emission. So people are actually, this is quite recent, like just last 3 years or so, people are starting to model this and trying to understand what could be the origin of this mega halo emission.
Thank you.
This particular mega halo that you are showing, is it an off-state or on-state? Can you tell that?
So these are merging clusters where we have found these mega halos. So certainly there is turbulence and reacceleration going on.
What type of galaxy Largo is having, like spectral or irregular shape, by looking into its redshift or light spirit?
Sorry, could you repeat? I missed the first part.
Can we tell about the galaxy Elgato is like spiral or elliptical or irregular just by looking at the redshift?
Okay, so this emission is on much larger scales than of individual galaxies. So this is coming from the intracluster medium itself. So which doesn't have any spiral or any particular kind of the galaxy morphology structure. So this emission is on much. A galaxy would be just a point in this kind of a plot. So one can quantify the shape of the emission. People do that to also, that is one way in which you can quantify the state of the cluster, whether it is relaxed or if the contours of this fitting, if they are more or less circular or elliptical, one would think that may be a relaxed system versus if they are more disturbed, you may conclude. So that is used, but in a different way than the galaxy morphology.
Thank you.
Okay, in the interest of time, let us move on. Let's thank Ruta again.